Hello everyone and welcome to Conf42 Cube Native 2025. My name is Srinivas Pagadala Sekar and I am delighted to share my experiences on a topic that sits at the heart of modern cloud operations on how large language models are transforming observability and accelerating resilience in platform as a service architectures. I've spent more than 14 years working across cloud native technologies, site reliability engineering, and software delivery. Over this time, I have witnessed how the scale and complexity of cloud systems have outpaced the traditional monitoring approaches. LLMs are not just a trend, they are rapidly reshaping on how we detect, understand, and recover from issues in dynamic environments. Today, we will talk through the key challenges of observability in modern platform as a service, how LLM driven innovations are changing the game, and how providers can deliver observability as a native service rather than just an add on. So let's dive in without any further delay. So, talking about the challenge of modern cloud observability. Observability in today's cloud world is anything but complex, even though the ask might be simple. With great power comes great complexity. Hope everyone agrees with me on this, especially if your mission is to build resilient platform as a service architecture. Organizations are pouring investment into public cloud platforms to gain agility and scalability. Teams are now embracing microservices and moving workloads onto cloud native platform as a service offerings to ship features faster. But with this evolution also comes with a steeper price. Complexity skyrockets. Legacy monitoring tools often just dump vast amounts of raw data, leaving engineers with dashboards full of noise but few actionable insights. When the systems fail, the gap between an alert and a fix can keep stretching, slowing down recovery in the meantime. In platform as a service environments, this complexity is further magnified. Services are deeply distributed and dependent on each other in an unpredictable way. A single issue can ripple through an entire ecosystem, right? And alerts frequently arrive without enough context for the engineers to respond quickly. And let's talk about the dynamic workloads. Think about an platform as a service offering with Kubernetes. Think autoscaling Kubernetes pods spinning up and shutting down within seconds. They make the failure landscape even more harder to track and resilient and to identify where the exact root cause is. Now let's take an example of a fintech platform as a service which is handling a very high volume trades application. Imagine a sudden spike in traffic hits and or a single service flatters and that causes transaction delays to cascade. Now your SRE team is flooded with alarms but lacks the correlated insights. Recovery slows down, downtime grows, and resilience suffers. I've seen these scenarios play out repeatedly, and they have convinced me that embedding smarter, self aware observability directly into the platform can fundamentally change how fast we can bounce back from disruption. So let's deep more into the distributed platform as a service environments. Imagine a healthcare platform as a service managing electronic medical records. Patient scheduling and clinical notifications are the core services of it. Services now must integrate flawlessly because it depends on the patient. It directly depends on the patient experience and even sometimes safety and other protocols as well. A seemingly a small update to one of the service can suddenly overload the event streams. It can choke dependencies and can also trigger cascading failures. Meanwhile, underlying infrastructure is also ephemeral. Containers scale in and out, and the IPs tends to change, and old troubleshooting assumptions are no longer hold good. So this reality underscores the urgent need for observability to evolve. Platform as a service offerings can no longer treat resilience as a bolt-on feature or something that the customers can figure out themselves. Instead, Observability must be integrated, it should be always on, it should be context aware, and also be capable of accelerating detection and recovery the moment this disruption begins. Now, with that, let's jump on to the evolution of observability. Observability has come a long way, but it's been a very slow climb. We started with basic infrastructure monitoring, where CPU graphs, memory usage charts, and simple alerts were in place. These worked well and good when the systems were monolithic and failures were easier to isolate. Then came the three pillars approach in the DevOps era, where metrics, logs, and traces gave us more depth but still required human correlation and interpretation. So, tools like distributed tracing and chaos engineering improved proactive testing, but they still demanded manual effort. Now, with AI and LLMs, we are entering into a new era. These models can ingest and interpret massive telemetry streams, correlate events in real time, and explain what, why, and how an incident took place rather than humans tackling this all alone. So, for platform as a service providers, this locks a new value proposition: observability as a built in intelligent service. The platform itself can proactively reduce downtime and it can guide recovery with no separate stack for customers to manage. Now, let's take a look at the large language models, which is the new paradigm. LLMs break the traditional rules based approach to monitoring. Instead of static thresholds or hard coded alerts, they understand the context. They excel at correlating diverse data sources like metrics, traces, and logs, even deployment histories, to explain why something is happening and how to resolve it. Imagine an e commerce platform as a service during a Black Friday rush. Latency spikes in the checkout service. A conventional alert tells you only that the latency is high. But on the other hand, an LLM can, however, dig deeper, linking a recent deployment, a sudden memory spike in one of the service, and an abnormal error pattern in another. Then surface a clear, actionable remediation to roll back or scale up. So in this case, the recovery time shrinks dramatically. This agility also enables platform as a service vendors to often offer a tenant specific LLM powered insight right out of the box. Customers don't need to build or fine tune their own models. Resilience becomes a part of the platform itself. Now, let's take a deeper look into the key capabilities that an LLM enhanced observability model can offer. So, they can offer automated root cause analysis, correlating telemetry across layers to rapidly pinpoint why a failure occurred, a remediation guidance, where suggesting or even executing recovery steps based on learned patterns, and continuously improving as it observes your workloads over time by adaptive learning, and comes in, and it can also decide when to escalate to humans versus self-heal, cutting the manual delays with intelligent automation. Picture a logistics company hit by a routing outage. An LLM not only flags the anomaly, but it can also help to analyze the patterns and propose or even auto execute rerouting strategies. Recovery that could have taken hours might now just take minutes. So let's take a look at how this can be implemented in an implementation approach. So this can be implemented in the following ways, like where you can start by integrating your alerts. You can feed your LLMs with existing monitoring signals and enrich them with context so alerts become more meaningful narratives rather than just being noise. And the LLM models can also be trained based on specific domains. So it can be fine tuned based on your platform's telemetry or deployment histories and failure patterns to improve accuracy. And it can also do predictive insights. We're moving away from reactive alerts to forecasts and also catching failing nodes or bottlenecks before they impact the tenants. You can also give engineers a chat like interface to ask why this latency is spiking and get a clear, context rich answer with a conversational interface. And you can also correlate or link seemingly unrelated signals like API errors, pod churns, or config changes to stop cascading failures early with deep correlation. I've read articles about this that in a media streaming platform as a service environment where LLM connected playback glitches to recent API throttling, helping engineers to fix the issue in minutes instead of hours. Now, after the implementation, the important part is what is the actual outcome? What could be the benefits of it? So, before an LLM integration, the mean time to resolution was taking long, alert fatigue was real, and the recovery relied heavily on expert engineers piecing the clues together. And after LLM adoption, resolution times dropped down dramatically, in some cases to under even 10 minutes, and where it also had a positive impact on less false positives, due to which like the productivity increased and the overall reliability improved. By baking this into a platform as a service, managed service, providers can now standardize resilience gains across all tenants, not just those with the elite SRE teams. Now let's take a look at a technical implementation framework that can outline the steps of what can be done to implement this. So start with your data ingestion and normalization, where you can pull your telemetry from metrics, logs, traces, and even CI/CD events. Clean and sanitize the data with a rich metadata, and also choose models and fine tune for platform specific workloads, for example, like scaling patterns or Kubernetes churns, and ensure low latency inference, where you can optimize the LLM. And you can also do insightful insights on delivery, where tailored outputs for each persona. Instant remediation hints for SREs, where summarized health and trends for developers or even managers. And the most important part is the technical toolchain integration, where you can expose the results via API, dashboards, or even platform consoles that the users can consume insights natively. And let's talk about a more important topic, which is the evaluation methodology. When introducing LLM driven observability into platform as a service architecture, it is always essential to have a structured evaluation approach to prove its value before wide adoption. A practical evaluation offering can include four complementary methods. One is controlled experimentation, where you stand up a test or a staging environment that mimic production in a multi-tenant Kubernetes cluster or like a service mesh, and where real telemetry pipelines are present. And you can inject these failures such as like pod crashes or cascading service degradation or even traffic surges. Now you can compare the performance of your existing observability stack with the LLM enhanced system under the same controlled events to even get a more clear or reproducible results. And once you have that in place, next is to do a quantitative analysis where you collect hard metrics like mean time to detection and mean time to resolution, and also the false positive rates to actually understand the accuracy of the root cause detection. And you should also monitor how quickly the system detects the trigger and correlates the signals together and guides or executes remediation. A well instrumented test often shows significant reduction in MTTR, that is the mean time to reduction, when LLM insights are added. Next comes the qualitative analysis. You engage the SRE and the DevOps teams who work directly with the new system. You can use structured feedback or sessions or surveys to capture changes in alert clarity or even the cognitive load and trust in recommendations. This human centered lens highlights whether the AI explanation are actionable and understandable, which is critical for adoption. Then comes the statistical validation, where you apply the statistical testing, example t-tests, or you can do a A/B testing, one with the traditional model and the other one with the LLM enhanced model, and also can do effect size calculations across multiple incidents to ensure observed improvements aren't just random. This step transforms raw results into credible, data backed evidence so that the new approach truly accelerates resilience. By combining controlled experimentation, quantitative KPIs, and human feedback, the platform as a service providers can confidently validate that an LLM powered observability delivers measurable resilience gains before scaling it as a core service. So, another important feature that we need to talk about is the privacy, security, and ethical considerations. Once evaluation is complete, more focus should be given to privacy, security, and ethical implementation. Trust is essential, right? So, when we talk about privacy, collect only what is actually necessary, anonymize it wherever possible, and design the data pipelines to comply with regulations like HIPAA or GDPR. And in terms of security, guard the model against misuse or data hallucinations or data leakage. Keep the critical remediation steps human verified wherever it is appropriate. And the most important part is ethical. As we all know, like AI and LLM has its own governance, and most of the systems, specifically in healthcare, government, or finance, they have their own regulations on how AI and LLMs can be used. So, in this case, mitigate bias in model training and ensure that the outputs are explainable so engineers can trust the recommendation. By addressing these from the start, a platform as a service provider can confidently offer observability as a service without compromising compliance or user trust. So let's talk about the future directions on where we are headed. So looking forward, we are heading towards a fully self-healing platform as a service capability, except multi-model inputs like logs, metrics, traces, video, or voice to enrich the diagnostics. And industry specific models will give domain tuned resilience, like, for example, the healthcare versus fintech or versus gaming, etc. And let's talk about federated learning. We will allow sharing intelligence across tenants without leaking sensitive data. And let's talk about edge aware observability, where computational aspects and reachability is limited, where it can adopt to a hybrid model and a very lightweight LLM based model that can serve edge aware observability as well. In terms of resilience, it will become proactive and predictive by default and no longer a reaction, but it should be an intrinsic platform capability. Now, let's talk about a practical implementation guideline. So, for those planning to implement, the first step is to prepare your infrastructure. Always ensure that you have enough compute and memory for LLM inference workloads, and strategize on your data. So, you need to prioritize clean labeled telemetry, sanitize the data in such a way that can be fed into the model as a baseline in vector databases so that the model can seamlessly respond back by looking at the semantics of your data. Next is training your teams by upskilling the ops team on AI driven workflows. And before you get started, once you have a baseline ready, The next step is to pilot by starting small, one service or a failure mode, and then expand gradually. You can also minimize the disruption with well-planned change management with smooth integration, and also keep measuring gains and refining automation with continuous monitoring. So these steps help platform as a service vendors embed LLM observability without derailing existing operations. So now let's wrap up. Let's talk about like how LLMs are not just improving observability. They are redefining resilience at a larger scale. By embedding these capabilities directly into platform as a service offerings, we can now dramatically cut down downtime, reduce operational burden, and can also deliver reliable self-healing platforms to every tenant. Thank you for joining with me today. I would love to continue the conversation. Feel free to connect with me on LinkedIn if you are exploring or implementing LLM driven observability. Thank you.